Uh, Good morning, everyone. I hope I am audible and visible too. Just okay. So, ma'am, can I get started?
Yes, yes, please.
Yeah. Uh, Hello everyone. Good morning. Myself Suhas Adiga. So today I'll be talking. My presentation will be mainly on sequences and series of functions and uniform convergence. But I have named it as real analysis in a glimpse because I'm giving a short recap on what happened in the past two lectures also, as it is important to know for my presentation today. Let's get started. Let's So mainly I'll start with an introduction on what is real analysis, followed by a short recap, and then on what is sequence and series of a function, and then followed by convergence of sequence, and then convergence of series, and finally the power series. This one is actually important more in complex analysis than in real analysis. So let's get started. So, what exactly is real analysis? So, real analysis is a field in mathematics that deals with the study of real numbers mainly on seeing how they behave. But real analysis also has wide range of applications. Mainly, the calculus which we have followed has its foundations or roots in real analysis. So, it is a hardcore a theoretical subject in mathematics, which mainly involves proving many things which we unknowingly use in like in our life, like in solving differential equations sometimes we make use of power series, right? But if power series converges to that solution or not, we check it using real analysis. So real analysis is actually considered to be one of the most difficult topic, but yes, if one can study it with interest, it is not so I'll try to make it as easy as I can. Analogous to real analysis, if you are a cricket fan, before the toss, you would have seen some pitch analysts who would have come and given a report on the pitch, right? So, in a mathematician terms, if you consider pitch as a set, like a pitch in Bangalore, a pitch in Delhi, a pitch in Kolkata, a pitch in Mumbai, as a complete set, then if you have its behavior, like how it behaves, like if it is a spin track or a dead track, then you are making a study of it, right? So in mathematician point of view, even pitch analysis is a kind of analysis, right? So similarly in real analysis we deal with the study of real numbers. So let's go to the next slide. So I'll try to give a short recap. Before that, let me just say one fact. Before right? A set of real numbers, if it is like this, we have first natural numbers, followed by whole numbers, followed by rational numbers, and then a set of irrational numbers, right? And this is the set of real numbers. So real numbers has almost all numbers. So actually let's see how actually the real number concept actually came in. So the elements in R, this notation is for real numbers and this is for uh, rational numbers. So the elements in R which are not in Q is termed as irrational numbers. So the motivation to this was actually came to Greek mathematician Pythagoras when he actually couldn't find the square root of 2. This is mainly because when he was working on this right angle triangle with its sides 1 and 1, he was not able to exactly compute what root 2 is equal to. So that is how the real numbers and irrational numbers actually came in. So to simplify irrational number, the new set real number was actually introduced. Just a minute, I'll reshare it. Yeah. If you see, let us look at some of the important definitions that are needed to know. So, for that, let me actually show you with an example what one means by epsilon neighborhood. So let's say we have a plot of sequence of some real numbers. So that is given by an equal to n by n plus 1. So we will plot an versus n graph. So let's say at n equal to 1, this will be 1 by 1 plus 2, that is 1 by 2. For n equal to 2, it will be 2 by 3. For n equal to 3, it will be 3 by 4 and so on, right? So I'll plot like this. At 1, L equal to 1, it will be 1 by 2. L equal to 2, it will be 2 by 3. L equal to 3, it will be 3 by 4. You can clearly see that it is this is the curve, and I choose some epsilon, okay, which is greater than 0. So this must be always true. It should be always greater than 0. Let me just take epsilon equal to 0.35, but L is equal to 1, okay. This you will get to know what when I say about convergence, why I took L equal to 1. So when I take 1 minus 0.35, this will be that point, and you can clearly see that from this point onwards, that is from n equal to 2 onwards, everything lies in this region L between L and L minus epsilon, right? So I say that an belongs to L minus 0.35 to L plus 0.35 for all n greater than or equal to 2. So that you can see, if I had taken an epsilon in such a way that L minus E would have been this line, L minus epsilon would have been this line, then I would have said an belongs to L minus epsilon comma L plus epsilon for all n greater than or equal to 1, right? So that is what I mean by that. So, so I hope about that it is clear. So let me go to next. So here you can see that I have some plot like this, and I have taken now epsilon to be 0.1. So this is that L minus 0.1 line and L plus 0.1 line, and this is actually outside only, okay. This point is actually looking big, but you can clearly see that after n equal to 7 onwards only, it is lying between L equal to 1 and L minus 0.1. So I now write it that it is for n greater than or equal to 7, right? So I hope this is clear. So if we have to mention it in notation wise, we represent it like this, like V epsilon of A such that X belongs to R, that X minus A less than epsilon. So this is called epsilon neighborhood of set of A. So let me now take a set minus 2, minus 1, 0, 1, 2, 3, 4. So first observation, tell me the terms which are having minimum value and maximum value. This term has the maximum value and this has the minimum value. So this is actually a lower bound and this is actually an upper bound. So the upper bound, the least upper bound of the set is called as a supremum, whereas the greatest uh, lower bound of a set is called as an infimum, okay. So this is clear. So for this set, both supremum and infimum exists. If supremum exists, then we call it as bounded above. If infimum exists, if we call it bounded below. If when it is bounded above and below, we call the set is actually a bound set. So let's see one more example where we are having a set from minus infinity to 4. So again, let's see the term having maximum value and minimum value. Maximum value is for 4, and there is no number which has a minimum value, right? So supremum here is 4, but infimum does not exist. Though it is bounded above, we cannot say it is a bound set. We term it as unbounded. So let's say one more set from minus infinity to plus infinity, okay. So again, here there is no minimum and terms having minimum value and maximum value. So both supremum and infimum does not exist. So clearly this set is unbounded. So, so let me already Preetpal has already introduced you about sequence of a real numbers. Let me just go through it quickly. So a sequence of real number is a real valued function defined on the set of natural numbers, that is f maps from n to r. So if there is some term an which is actually a function of f of n, for all n belongs to n, then we write the sequence as f equal to an or a1 a2 a3 in a closed bracket. So remember, this is not the only notation. You can write it as A1, A2, A3, so on till AN, or you can write it as in curly bracket A1, A2, A3, so on till AN, or you can just write it as AN, or you can just write it as curly bracket AN, or there is one more notation which is used in some books in a arrow bracket, okay, A1, A2, so on till AN, or you can just write it as simply an, okay. So this is how we represent a sequence of real numbers. So a sequence of real number can also be called as a real sequence. So mainly a sequence of real number can be of three types: either it is convergent, divergent, or oscillatory. So let me actually show you what exactly I mean by convergent, divergent, or oscillatory, okay. Just a minute. Huh. So let me just try to plot a sequence an where n goes from 1 to infinity is equal to 1 by n. So the terms of the sequence will be 1, 1 by 2, 1 by 3, 1 by 4, followed by 1 by 5, so on, right? So it's an infinite series. So I have plotted 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, 1 by 8. Clearly you can see that it is going almost towards zero, right? For any when you go almost, it will be almost in tending to reach this line. So that is what we mean by convergence. So if you would have seen a convex lens, then you would have called it as a converging lens, right? Because the light coming from infinity goes towards one point, right? But while for concave lens, the light from is going towards infinity, but it is appearing to coming from one point, and then we call it as divergent, right? So let me show an example of a divergent sequence also. So I have an equal to n from n equal to 1 to infinity given by n. So I'll plot it, and at n equal to 1 it will be 1, at n equal to 2 it will be 2, n equal to 3 it will be 3. So it is a straight line. Like it appear, though it is not continuous, it will be only a dot. It lies on a straight line, right? That is what I can see. So you can see that it is not tending to reach any point, but it is going towards infinity. So if it is, if this is going towards infinity or something, then we call it as divergent sequence. So now I have one more sequence given by minus 1 power n. So for n equal to 1, it will be minus 1. For n equal to 2, it will be plus 1. So you can clearly see that for every odd number, it will be minus 1, and for every even number, it will be plus 1. So clearly, it is oscillating between minus 1 and 1, right? So we call it as an oscillatory sequence here. So I already gave an example about convergence. So you know that the motivation behind convergence is that it is tending to go towards one point, and we have an operator called limit in mathematics, which will help us to find the behavior of some sequence or some function when it is going towards some point, right? So I can clearly say that if it is converging, then limit when n tends to infinity an should be something, this should be defined. If this is defined, if this gets some fixed value, then we call it as a convergent sequence. If this limit does not exist, or gets, you get infinity or something which is not defined, then we call it as uh, a divergent sequence. So we can say about convergence in other terms also. A sequence an in a set of real number is said to converge to a real number a if for every epsilon greater than 0 there exists a positive integer n. This is actually dependent on epsilon. Okay, so an minus a is less than epsilon for all n greater than or equal to n. So this actually Prithpal has given derivation also for this, so proof for this, so I'll not go to this in detail. So in this case, we call the number a, this a, as limit of sequence. So this is an, this is equal to a, this is what we mean, and then we call it as, then we call the sequence an is a convergent sequence. So convergence can be of two types, the first one being pointwise convergent, and the second one being uniform convergence. So we look about these two in convergence of sequence. I'll not cover it here, but a spoiler, every uniform convergent sequence and series is a pointwise convergent. Okay, so let's now look at series of real number. If we already have a sequence of real number given by an. I have used this notation, but if you are comfortable with this, you can use this also. From n equal to 1 to infinity, then the associated series with this sequence will be given by sigma n equal to 1 to infinity an. Okay, so this will be equal to a1 plus a2 plus a3 plus so on. Okay, but to discuss about convergence of a series of real numbers, we actually need something called as sum of partial sums. So this sum of partial sum actually leads us again back to sequence. So for a series, your steps are to prove something is convergent, your steps are same as that of a sequence. So for a partial sum, then we represent a partial sum by the denotation, by the notation Sn. So from n equal to 1 to infinity. So you can see here, then Sn is given by a1 plus a2 plus a3 plus a4 plus so on till an. So if you have S1, it will be A1. If you have S2, it will be A1 plus A2. So this is clear, right? So actually, the motivation for an infinite series comes from a paradox given by one of the famous Greek philosopher by the name Zeno. Actually, the thing is, there are once a tortoise comes to a warrior called Achilles. So it challenges him, saying that they both has to race, and tortoise can actually easily win. But tortoise here can go at speed of 5 yards per second, and Achilles at 10 yards per second. But tortoise says that tortoise can defeat Achilles if he is given an advantage of 10 yards. So this is the start line, x equal to 0 for Achilles, x equal to 10 is the start line for tortoise, and the finish line is at x equal to 100. Okay, so it's a 100-yard race. So let's look at it in the way Zeno actually argued. Yeah, so you can clearly see that this is at t equal to 0, and this is for tortoise at t equal to 0. So at t equal to 0, the difference between them is 10 yards, right? At t equal to 1, uh, tortoise would be at 15, and Achilles would be here, right? So the difference now is 5 yards, that is 10 by 2. So after another half seconds, tortoise will be at 17.5, uh, right? And Achilles would be at 15. So they are now again at a difference of 10 by 4 yards, that is 2.5. Similarly, after another 1 by 4 seconds, the difference will be 1.25, and then followed by 1 point, after adding 1 by 8, it will be 0.625 yards. So Zeno's argument was, when you take the time in this form, that is here, the difference will be 10 to the power 10 by 2 to the power n. So so this was an infinite series, right? So Achilles' argument was that whenever you have an infinite sequence, the answer will also be infinite. So accordingly, then for this to be 0, it will take infinite time for Achilles to reach tortoise. Hence, tortoise would easily win, right? But let's see if convergence is of any use here. So we have Sn is this, and then we subtract Sn by half Sn. So we get it as 1 minus 1 by 2 power n plus 1. So it will be Sn by 2. So I multiply 2 here. Now I apply limit Sn tends to infinity, Sn when n tends to infinity, and same on the right hand side, and you can clearly see that it is at 2 seconds, right? So this will be 2 because this will tend to 0. So it will be 2. This answer will be 2. That is at time t equal to 2, they will that is Achilles will be cover 20 yards, and he'll be in par with tortoise, right? But if you would have done this question analytically also, one could have done, but Achilles didn't think that way, because after 2 seconds, tortoise would have come here at 20 yards, and even Achilles would have come here, right? So basically at t equal to 2, Achilles is overtaking tortoise, but Zeno was not able to explain it. So Zeno's thinking was wrong. So we say a series is convergent if its partial sum Sn when n tends to infinity is equal to S. Okay, if this S exists, then it is convergent. If not, it is divergent. So some of the conclusions I have taken this from Preetpal's slides. So limit of a convergent sequence is always unique. That is, this limit has always one value. So if you get something S1 and you also get something S2 as a limit, then S1 should be equal to S2. Okay, and a convergent sequence of real number is always bounded. So let me go to my topic now, a sequence of a function. So you already know what is a sequence of a real number. Sequence of function is something which is above it, which will actually lead us to sequence of real number if we define some value for x. Okay, so we define, I'll read out the definition and then try to explain. So we have a function fn, which is a real valued function on a subset of R. So this is a domain. A is the domain here, which is a subset of real numbers. And remember, this should not be equal to a empty set. If you have nothing as a domain, then your function is not defined. Right? There will be no range actually. So then there exists n, which belongs to set of natural number, then we can give the sequence as curly bracket f1 comma f2 comma f3 so on till fn, right? This is called a sequence of a real valued function only. So this is the notation we actually use. We can also represent this again by this three notation I have used in a set of real numbers. So if I have a mapping, let's say this is f1, f2, f3 and so on. Okay, let me just erase this. So I have one, 2, 3, 4, so on. Then this is that function fn. For n equal to 1, it will be f1. For n equal to 2, it will be f2. For n equal to 3, it will be f3 and so on, right? Now again, if I operate with this with x, okay, if I give it, then this will give me a set of f1 of x, f2 of x, right? f3 of x and so on. So if I say this x is equal to 3, let's say, okay, then it will be this sequence will be f1 of 3, f2 of 3, f3 of 3 and so on, right? So then this is actually leading me to sequence of a real number, but here it is a sequence of a function. So sequence of real number is way before you get sequence of real number you obtain because you are defining x to be something, right? So let me look at some example. Let's say fn is equal to x and x it is given by x power n. Then fn of x is defined as x power n. So then we define the sequence of real function as f1 of x, f2 of x, f3 of x, f4 of x, so on till fn of x. And if you define, so this will be x, x square, x cube, x4, x to the power 4, so on till x power n. So let's say x equal to 2, then I get it as 2, 4, 8, 16, so on till 2 power n. So clearly this was a sequence of function, but when I define x equal to 2, this is a sequence of a real number, right? So you get this, right? So let me just say what is a series of function. Again, like series of real numbers, series of function again depends on sequence of function. So we have a sequence of function given by fn. It is again defined on a set A, which is a subset of R, and there is some n which is actually belong to set of natural numbers. Then the expression f1 plus f2 plus f3 so on till fn is equal to, this will be equal to sigma n equal to 1 to infinity fn, right? So this is called a series of a real valued function only. We let's take an example. We have a sequence fn. This function is defined by fn of x equal to cos of nx by n square, and this x belongs to x is in the set 0 to 1. So clearly this is a what we are saying, and this is a subset of R, right? So then we represent the series as sigma n equal to 1 to infinity fn of x, which will be cos of 1 x by 1 plus cos of 2x by 2 square, that is 4, cos of 3x by 9, cos of 4x by 16, so on till cos of nx by n square. So this is called a series of a real valued function on in 0 to 1. Again, if I say x equal to pi by 3, and then this will be a series of a real numbers, right? So let's see what do we mean by a pointwise convergence. So a sequence of function fn is said to be pointwise convergent if there is some x which is actually in the set A, then the sequence fn of real numbers is said to converge. Okay, so this is nothing but the convergence definition which I gave. So but here it is converging to a some function only. So if we have when n tends to infinity, fn of x tends to f of x. So let me actually go to an example again. So we have a plot here. Fn of x is given by x to the power n for all n belongs to n. Okay. So when we plot it with x, let's say for x n equal to 1, we get it as x. So this is that line. So do not, this diagram is not for scaling. So for n equal to 2, it will be x by 2. For n equal to 3, it will be x by 3. For n equal to 4, it will be x by 4. For n equal to 5, it will be x by 5, this line, and so on till x by n minus 1 and x by n. Clearly you can see that all these lines are actually tending towards 0, right? So this is a converging sequence of functions. Before we were looking at
real numbers, but now we are looking at functions. So all these functions are going towards zero. So in this case it is converging to zero. This is what we mean, right? So the pointwise convergence can also be given like this, that is absolute value of fn of x minus f of x. So this is that f of x is less than epsilon for all n greater than or equal to n, and this epsilon is always greater than 0. So let's look at some examples to prove the pointwise convergence. So fn of x is given as x square plus nx by n for all x belongs to R, right? So now we have to prove it is pointwise convergent. So let's try to simplify fn of x. So it will be x square by n plus nx by n. So that will be x, right? So this is fn of x. So we can apply limit when n tends to infinity, right? So this will be limit n tends to infinity x square plus n x square by n plus x, right? So clearly you can separate out this terms of limit. So it will be limit x when n tends to infinity plus limit n tends to infinity x square by n, right? So this, because the condition here n is tending to infinity, we can consider x to be constant and it comes out. So it will be x limit 1 n tends to infinity. So this will be x plus limit x square by n. You can bring x square out, and when n tends to infinity 1 by n, this will be actually 0, you know, right? So this will be x plus 0, that is x. So fn of x, this is the notation we actually use. Fn of x convert by one arrow, we mean it converges pointwise to f of x equal to x, okay? Or else you can write it like this also. Fn tends to fn tends to f equal to x point. So this by this you mean uh, it is converging pointwise, okay? Let me so this is the plot. So you can see that for all the functions are actually it is converging to one particular point here, or you can take any x, okay? Like you take some x equal to 0, you see that all functions are actually coming towards 0. And for some x equal to 4, you can see that they're almost somewhere here, right? So that is where it is converging to. So let's take one more example where gn of x is equal to x to the power n in the set 0 to 1. So this is the set A, which is a subset of R. So both are close in the interval 0 to 1, right? So for this we'll have to be kind of analyze it piecewise. So let's say I fix x equal to 1. So then it will be 1 power n, right? So gn of 1 will be equal to 1. So this sequence will be like 1 power 1, 1 power 2, 1 power 3, so on till 1 power n. So this is all the elements in this are 1, right? So this is actually converging to 1. So I'm saying here gn, when 1 it is 1, it converges to 1. So let us look at for again for 0, it will be again the set will be 0 0 0. So it is converging to 0, right? So let's look at it for the points between 0 and 1. So clearly if you have something like let's say 0.1 as x, then it will be 0.1, 0.1 square, 0.1 cube, which you clearly know is actually again going towards 0. So we have two things here. So gn of x converges to 0 for x between 0 and 1, and it converges to 1 for x equal to 1. So here the pointwise limit function is actually not continuous at x equal to 1, but still it is converging, right? The limit actually exists. If limit exists, we call it as convergent. We don't care if it is converging to same number or not, but if it is if the limit exists, we call it as convergent, right? So clearly it is converging, but it is piecewisely defined, right? So think about the convergence. This is actually a kind of homework for you. You can just think about the convergence in the set 0 to 2. So this is the function gn of x equal to x power n. So clearly at x equal to 0, you can see all the functions are approaching 0. And at x equal to 1, you can see it is approaching 1 again. So a third example, fn of x is equal to sine of nx plus n by n for all x belongs to R. So let's say f of x equal to 0 for all x belongs to R. Okay. So this is just an this is from again a limit n tends to infinity fn of x. So this will be limit n tends to infinity sine of nx plus n. So here it is, you have to be like, you have to think about it a little mathematically. A good what good use of some theorem would actually simplify things. So if we have sine of nx plus n, you know clearly that it lies between 1 and minus 1, right? So clearly I can say that sine of nx plus n will by n will lie between minus 1 by n and 1 by n. So when limit tends to minus 1 by n when n tends to infinity, or limit 1 by n when n tends to infinity, is clearly 0. So so this is f of x. So f of x is 0. That is what I have made an assumption here. Okay. So clearly, fn of x converges to f in R for equal to 0. That is what we can say. So also you remember, right? I gave one more definition, that fn of x minus f of x, the absolute value of this should be less than epsilon, right? So we are getting it as 0 here. So this is clearly what we defined, that epsilon is greater than 0. So this is the plot, how it looks. So one more example. Let's consider the sequence fn of functions defined by fn of x equal to n square x power n. So for all x which lies between 0 and 1. Again, this is same as saying this, right? Determine whether fn is pointwise convergent. So let us see at x equal to 0 how it will behave. At x equal to 0, this is clearly a sequence of all terms having 0, right? So fn is a constant and it converges to 0. So for a number between 0 and 1, then the function is n square x power n. So we will make a brilliant substitution for x power n. We can write it as e power n log x base e. So you know, from to prove to, I'll just show how this is equal to x power n. So you have e power n log x base e. So this is equivalent to e power log x to the power n base e, right? And you clearly know that whenever this is the case, this is of the form a power log x base a, this is equal to x. So clearly this is equal to x power n, right? So this is the substitution I have made, and let's see how log behaves actually. So when for the numbers between in the range 0 to 1, when x is between 0 to 1, you know, log x base is clearly negative, right? So again now, because it is negative, you can clearly say that it will be like n square by e power minus n. So e power n, n square e power minus n, or something like that, right? uh, it will be a negative number. So clearly limit n tends to infinity when fn of x is equal to 0, again for numbers between 0 and 1, right? So at n equal to 1, this will be, because it is n square x power n and x is equal to 1, we write it as n square 1 power n, n square 2 power n, 1, sorry, 1, wait. So the sequence will be n square, oh, wait. For n equal to 1, it will be 1. For n equal to 2, it will be 4. N equal to 3, it will be 9, and so on. And this is clearly diverging, right? Because limit n tends to infinity, limit n square when n tends to infinity is not defined, it is infinity. So this is not pointwise convergent in 0 to 1. So in the previous example you saw that it was converging to two different points, but still it was pointwise convergent. But here clearly in this set uh, it is converging and it is diverging too, so it is not a pointwise convergent, right? So will this same sequence be pointwise convergent if we exclude one? Anyone can give the answer. Hello. Hello.
Yeah, yeah, we can hear you.
Okay, ma'am, fine. So in this case, it will be pointwise convergent, because we are not defining, because this set is open at 1, but here it was closed at 1, right? So we are excluding this point, and hence it is clearly pointwise convergent. So this is how the graph looks. And you can clearly see that at x equal to 0, all functions are tending towards 0. And at x equal to 1, they are kind of tending towards infinity, right, along y-axis. So that is why we call it to be divergent at x equal to 1. So let's look at what do we mean by uniform convergence. So we have a function fn, which is again defined from domain is A, which is a subset of R, and it is the range is R. And again, we are clearly saying that there exists f, that it is pointwise converging from A to R. So this is already given to us. Okay. So then we say that the sequence fn converges uniformly on A to a function f if there is some epsilon which is greater than 0, and there exists a number n in the set of natural numbers such that for all x belongs to A and n greater than or equal to n, it follows this condition. So this condition you had seen in pointwise convergence also, but here there are few things which we are telling it is already existing, right? So to define to notationally we can represent uniform convergence like this. So don't consider this arrow, it will be two arrows. So fn of x then followed by two arrows. F of x means fn of x converges uniformly to f of x for all x belongs to A, or you can just write it as fn two arrows f. Okay. So let's see what is the difference between pointwise convergence and a uniform convergence. So in pointwise convergence, we were given an epsilon greater than 0, and the number n was supposed to be found after we have x in A, right? So n here was depending on x and on epsilon also. So, but here in uniform convergence, we find a number n which actually works for every x. Okay, in the set A, that is in the domain, it should work for all x. So n is independent of x in this case. So again, every sequence which is uniform convergent is pointwise convergent, but the converse isn't always true. Okay. So let's consider some examples here. So we have a function. I am taking the same example which I took in pointwise convergent. That is because I can save time in not proving pointwise convergence here. So we have the function fn of x equal to x square plus nx by n. We already proved this was pointwise convergent. This was converging to x, right? If you remember. So that is also clearly given that f of x equal to x. So we have to find out if fn converges uniformly on R. So because we know that it is already pointwise convergent on R, we can directly uh, consider this. That is x. We can see mod of fn of x minus mod of f of x. So that will be x square by n plus x minus x. This modulus should be less than epsilon, right? So this will be x and x gets cancelled. N is a natural number, it is always positive, and x square is also always positive because x is a real number, right? So this will be we can clearly remove the mod. So x square by n is less than epsilon for all n which is greater than or equal to n. So let's see if x belongs to R. If, like in this case, is it possible to have something like that? So let's consider if such n existed, then we can take x equal to for n equal because n is greater than or equal to n, we let us put n at n equal to n. Okay. So at n equal to n, it will be x square by n less than epsilon, right? So let us take x which is equal to root n. So x square will be n, right? So n by n less than epsilon. So epsilon greater than 1. So this is what we give. This is what we get, right? But we clearly defined epsilon should be greater than 0, right? So this is kind of contradiction to our assumption, because if the epsilon chosen was less than 1, then it is contradictory to our assumption here, right? So therefore this sequence does not converge uniformly to f on R. So this is what we can conclude. But think about this. What about uniform convergent if there existed some x in minus b to b such that n now is given as b square by epsilon? So you can clearly see that in case of uniform convergent, n is depending only on epsilon, right? But in case of pointwise convergent, it would have been a function, it would have depended on x and epsilon, right? So I'll tell you, it in this case it is uniform convergent, but do try it out yourself. Okay. So this is again one more question. Uh, we have the sequence of function sine of nx by root n. The of fn of x is given by sine of nx by root n. So we have to see if it is converges uniformly to f of x equal to 0 on R. So clearly, we had proved it. I guess we had proved for different one here. We had taken nx plus n, but that doesn't matter as a lot here. So let us that is already a pointwise convergent one. So we have fn of x. Let's find out f of x. It is given to be 0. So limit, I'll just show how. N tends to infinity, sine of nx by root n, right? You know, the sign of nx lies between 1 and -1. So limit 1 by root n when n tends to infinity is actually 0, right? So this is 0. So f of x is 0. We have sine of nx by root n under modulus. So this should be less than epsilon, right? So we have because sine nx is lies between -1 and 1, we can write it as 1. So 1 by root n. So 1 by root n is less than epsilon. You can clearly see it was equal, but I'm using less than, or this is less than or equal to, because this lies between sine of nx actually lies between 1 and -1, right? So that is why this the greater than or equal to term has come. So, and there exists some n which is in the set of natural numbers such that epsilon is greater than 1 by root n. So that is true, right? There can be any, you take n equal to 1, epsilon will be greater than 1. N equal to 2, epsilon will be greater than half. So that is not bothering us a lot. So here clearly fn converges uniformly to f equal to 0 on the set of real numbers. So this is this you can try it out yourself, but hint here is you can approximate 1 plus n square x square as n square x square, because when you are finding f of x, n tends to infinity, this one will be actually, you can approximate it. Okay. So there is one more a kind of ninja trick to find uniform convergence. This is called as a Cauchy criteria. So a sequence fn converges uniformly on A if and only if for every epsilon greater than 0, there exists n greater than 0, such that for all n greater than or equal to m, for n equal to 1, here we have defined n can be anything, right? N can be any natural number. So in that case, it will not be a contradiction that epsilon is greater than 1. So we define Cauchy's criteria as modulus of fm of x minus fn of x is less
Sorry,
than
what was
epsilon.
the question Samarth had?
Ma'am, that was for
In the
the,
last slide, ma'am, it was little. Yes. Oh,
yeah.
yes, yes, ma'am.
He said like if n is equal to 1, then epsilon is greater than 1, which is actually contradiction to our assumption that epsilon is greater
No,
than
but
0.
the definition says that for every epsilon greater than 0, there exists some n greater than or equal to capital N, such that whenever small n is greater than capital N, then fnx minus fx should be less than epsilon. So here the small n will be always greater than 1. That is all. Right?
Yes, ma'am.
So we have to just see that after certain value of n, all the values of the series sequence, they are converging to some value. They are at a distance less than epsilon, then the limit value for some n greater than some capital N. So that capital N can be, it is not that capital N, you are not fixing capital N. What you are fixing is epsilon. That, so you actually, that for every epsilon greater than or equal to root n, there will exist some epsilon, there will exist some small n, right?
Yes, ma'am. I do epsilon by 2, and similarly for this is also less than epsilon by 2. So when you add these both these two, it will be less than epsilon, right? So this condition I have proved it here. So I'll just tell some of the consequences of uniform convergence that will be actually useful. Though it is of not much use here, but knowing that would be really good. So if we have a function fn, which is actually from a to set of real number, is a sequence of function, then fn converges uniformly to f. Then if fn is continuous, then f is also continuous. And similarly, if fn is bounded uniformly, if fn is uniformly convergent on a, then f is actually bounded on a. And if the sequence fn is Riemann integrable function, which actually converges uniformly, then f has a limit. Then the limit f is also Riemann integrable. So these three consequences will be of a great use. So let's now go to convergence of series. So suppose we already know that for a series you need to have a sequence of functions, right? So we have a sequence of function called fn. Again, the domain is domain is A, and range is in R. So let Sn be the a sequence of partial sum. Again, partial sum has a domain in A and range in R. Then partial sum is actually equal to here f1 plus f2 plus f3 so on till fn, right? So clearly, you can say that this is the partial sum, and the series is just do not look at this. This might confuse you. We say that this actually converges to s of x. Then limit Sn when n tends to infinity is equal to s of x. Okay, Sn of x is equal to s of x. So this is what we mean by pointwise convergence. Okay, so this is again same like how we did in series of real numbers, right? In series of real numbers also we took the partial sum, and when n tends to infinity it converges to some s, right? So this is what we mean by pointwise convergence in series. Then for uniform convergence we again have the same condition. Just do not get confused by these terms. Sequence f series Sn converges uniformly to s if Sn of x minus s of x, the absolute value of this is less than epsilon, right? Or you can say that in terms of Cauchy's criteria, you can say that Sm of x minus Sn of x modulus is less than epsilon not epsilon, right? So this is what again you can see that everything is almost similar, like sequence of a function. The definitions almost look like that, but here you deal with partial sum, whereas there you are dealing with sequence of function directly. So a proof to this, whatever I wrote here. So Sn of x is given by summation of fk of x from k equal to 1 to n. So it will be f1 of x plus f2 of x, f3 of x, so until fn of x. So the sequence Sn, we have the sequence Sn, right? The sum of the sequence of partial sums. So therefore, we say that this Fn converges summation Fn, or the series converges uniformly if there exists epsilon which is greater than 0, and there exists n also, such that Sn of x minus Sm of x is less than epsilon. So we are assuming n is greater than m. Okay. So let's go to the proof. You can write Sn of x minus Sm of x. So rather than complicating with n, some arbitrary n and m, I'll take it as S4 minus S2. Okay. So in this case, S4 will have terms F1 plus F2 plus F3. Oh, sorry. I, so it will be, uh, sorry, it will be, just a minute. It will be f1 plus f2 plus f3 plus f4, right? And s2 will be f1 plus f2. And when you subtract that is 1 minus 2 will give you f3 plus f4. So if this was n and this was m, then this is m plus 1 and this is m plus 2, right? So, or you can say this is n also. clearly the sequence goes from m plus 1 to n. So I can write this as sigma k equal to m plus 1 to n fk of x also, right? So uh, so Sn of x minus Sm of x should be less than epsilon. So then we can actually, like how we had Cauchy's criteria, we have one more ninja trick to prove some series is uniformly convergent. That is called Weierstrass M test. So if we have a sequence of functions fn, and fn maps from a to r, and suppose that for every n greater than n there exists mn. So this is some number mn which is greater than or equal to 0. So there are two condition 1 and condition 2. Condition 1 is that the modulus of fn of x should be less than or equal to mn for all x belongs to a. And condition 2 is that summation of mn should converge. Okay, so let's make this clear with some examples. You can see how easy this is. Like if you know this, you can easily prove uniform convergence of a series. So let's take some series sigma n equal to 1 to infinity sine of nx by n square. Okay, so this is fn of x, right? This is the function. So clearly sine Sn of x is equal to sine of so this should be fn of x. So Sn of x will be sine x by 1 plus all that series, right? So when limit n tends to infinity, sine of nx by n square, this is clearly 0. So because this is 0, the limit exists, it is convergent. So l- clearly Sn of x, this was s of x, right? So we have s of x equal to 0. So Sn of x minus s of x should be less than epsilon. That will be modulus of sine nx by n square. Again, you know that sine nx is lies between 1 and minus 1, so it is less than or equal to 1 by n square. So clearly there exists n such that 1 by n square less than epsilon, right? So if there is some n greater than or equal to n, then this converges uniform. This is again same like how we proved uniform convergence uh, uh, in the sequences, right? So let's take the same example, but we'll make use of Weierstrass M test. Okay, so we will take fn of x equal to sine of nx by n square. So this you clearly know that it is less than or equal to 1 by n square. So let's say this is that mn. Okay, so mn is 1 by n square now. So let's just say it. Okay, so then we have to prove that the second condition was that the summation mn should be convergent. That is, summation of 1 by n square is convergent. So if you know this, in Anirudh's lecture, he took something called as P series, right? That is sigma 1 1 by n power p is convergent for all n greater than 1 and divergent for all n sorry, n greater than or equal to 1 and wait, this should be p. So for it was convergent for all p greater than or equal to 1, and it was divergent for all p less than or equal to 1. So clearly for we have p equal to 2 here, so it is convergent, right? So this summation is convergent. So both the condition is satisfied, and hence we say that it is uniformly convergent on 0 to 2 pi. So this is what okay, I was wrong. It was not p greater than or equal to 1, it was p less than or equal to 1. It is divergent, and it is convergent if p greater than 1. So let's look at one more example. We have the series given as summation n equal to 1 to infinity 1 by n plus x square whole square, right? So this is fn of x. We'll take the modulus of it, and for all x belongs to r and n belongs to n. So clearly we know that uh, n plus x square is greater than or equal to n, right? Because x is some real number and x square is always positive. So n plus x square is greater than uh, n, actually greater than or equal to n. So when you square it, n plus x square whole square is again greater than n square. So when you take the denominator it to the denominator or divide by 1, then it will be 1 by n plus x square whole square will be less than or equal to 1 by n square. So approximately we can say this. So let's say this is mn, and again let's just say that, and if this is mn, it should be convergent, right? Again, this is the p series one which we did, which I said that for p greater than 1 it is always convergent. So p is 2, so clearly this is uniformly convergent on r. So let's now come to the last topic of my presentation today, that is power series. So this power series is actually important in complex analysis more than in real analysis. So any series which is of the form an x power n or an x minus c whole to the power n is called, from n equal to 0 to infinity, from n equal to 0 to infinity, we call it as a power series. Okay, so here remember this an is some function of n, so it can be like n into n plus 1 by n factorial. This can be an, or an can be just simply n or something. Okay, so when we expand this power series, we get it as a naught plus a1 into x minus c plus a2 into x minus c whole square plus a3 into x minus c whole cube till infinite terms. Okay, this is an infinite series. So what is this point c? This point c is called the center of power series. So the center is something like we used to define the center of Taylor series, right? So something like that. And the sequence an is called the sequence of coefficients of power series. Okay, that is it. The sequence is a1, a2, a3, so on. Okay, so this power series also converge at its center c. That is, we assume that c is equal to 0, that it is always centered at 0. So here is one example of a power series, that is summation n equal to 0 to infinity 2 power n by n factorial x power n. Okay, so uh, let's now consider a power series. Let's just assume c is 0. Then sigma n equal to 0 to infinity a n x to the power n. So if there is a positive real number r such that the circle mod of x minus x naught is equal to r, so this consists all values of x for which an x power n is convergent. Okay, so then the circle is called as the circle of convergence, and this r is the radius of convergence. That is, we mean if there is a circle, within this in all points it is, this power series is convergent, and you go outside it, it is not convergent. So if power series converges only for x equal to 0, we call it as nowhere convergence. If it is if it converges for all x belongs to r, then we call it as everywhere convergence. Okay, so we have we can make some conclusions from radius of convergence. Let's consider a set S which consists all x, which is actually R. This R is radius of convergence, not the set of real numbers, such that this series actually converges. So if S has only, if S, the element in S is 0, then the power series will only converge at the center 0. If this if this set has element r, in this case the power series converges at every x which is actually r. Okay, at every x which is the radius of the circle. But if there is a case, if the set has elements which is not in r and not a 0 also, then it is convergent if mod x is less than or equal to r, or we can say the supremum of the set S, or we can say that it is divergent if mod x is greater than r. Okay, so that is what we can conclude. uh, you can clearly see, conclude this from here, right? I said that circle at radius it is convergent for all x belongs to r. For something 0 it is convergent at the center, and for any terms in between it is also convergent, right? So that is what I said, that is what I meant in the previous slide. So this radius of convergence actually can be given like this. If you clearly see that this is something what Anirudh explained, something called as root test and ratio test again of series. So the radius of convergence is given by 1 by r equal to limit n tends to infinity modulus of a n plus 1 by a n, or it can be given as limit n tends to infinity a n to the power 1 by n, or this can be also written as limit root nth root of supremum of s when n tends to infinity, because we have already said how we get the supremum of s, right? So that's it. Thanks for your patience and listening. So if you have any doubts, you can ask. So these are some of the references I used. You can refer Bartle. Most of the things I've taken from Bartle only, and that's it. Yeah, thank you.
Yes, any question? Thank you, Suhas. Any
Thank you.
question?
No, ma'am.
So Suhas made everything so clear that there is no doubt. Yes. So then we are now ready for doing these things in the complex analysis. So the statements are going to be almost similar, only that we will be using these for the complex numbers. So
Ma'am,
Uh,
just a thing. If anyone wants the access to the PDFs the PPT and the notepad I used, you can just
no,
check
no,
out the
not
link.
now. Don't give it now. First, let me do the assessment. Not now. After
Okay,
some
ma'am.
time. Okay.
Yes, ma'am. Fine.
So I was waiting for actually this presentation. So now I will give the assignment that I have made, which will be updated from time to time. At the moment, there are only five questions in that I have already told you in the class. Three are these sequence series and this series of functions, and one was on stereographic projection and one was on mapping. So, and I have given the roll numbers in the assignment, the people who are supposed to do these questions. And there is a deadline for every question. There will be a different deadline. As we go along, I will be giving more topics. Okay, because these presentations were decided suddenly, so I had not thought of that. But now, after thinking, I thought that I will be giving the same question to a number of students, and the one who will be doing the one whose presentation is very good, or if there are two people combined, their presentation is good, then they will be asked to give the presentation. And there are some for Suhas, Anirudh, and Pritpal. There, I mean, besides what all you have covered, that is theory. So that part of your assignment is ready. But I have also added certain questions in that, like some specific examples where you have to prove convergence or divergence. And there, so you will have to update. I mean, this you can, so you can, if you think that whatever has been asked in the assignment has been covered in your presentation, then you can simply upload your presentation, and along with that you can upload another file which will contain the answer to those questions. Okay, so that you don't need to write this part again. And I think almost all that is covered. But if you think that some question is not there, then you can add that within the presentation, and the questions where you have to solve something, that part you can submit as a separate file. And so I think I have kept 10th of February, uh, or because for you it is almost ready. So for the other questions, 10th of February is the deadline. But for the other students, because there are 70 students in the class, so there will be uh, deadlines will come later. The questions that will be added later, the deadlines will also come later. So the same assignment I will update. That is one thing. And you will also get your lab assignment today, and you can start submitting that. Plus there will be a test. I had written you on the WhatsApp group yesterday night that there will be a test within February. We will have the first test, and that will include whatever we will be able to cover just a week before that. So I will tell you the syllabus of the test when we are approaching that date. But certainly whatever we have covered till now, that will be there. And I'm sure I will be able to finish the analytic functions and the elementary functions by then. So only the integration part will be left. So that will be covered in the next test. That is the, I think, ideal place to hold a test, because the other half will cover all these Cauchy's, all these integral theorems, and how to perform the real integrals using the complex ones. Okay. And today's lab class will be at 2:45, because Nimi ma'am wants to take the class at 12:45. Fine. Anything else?
Ma'am, we'll have to make the presentation in groups or
No, no,
individually.
there is no presentation. You have to just submit the assignment, and the student who will be, if I feel that there is someone who has submitted is like worth presenting to others, so that everyone gets to know about. Because what I'm giving in these assignments are the topics that we will not be covering in too much detail in my lectures. They will be slightly off the track because they are not too I mean too much details is not there in the syllabus, or there might be a topic which I feel that you can do on your own, and it will be good to do some literature survey on your own and then discuss. So such topics will be given. So you just submit it as an assignment first, and if someone does very well, then or whoever does the best will be asked to present. And the assignments will be can be done maximum in the groups of two, not more than that. But and you can do it alone also. So these three students have essentially done it alone only. So for the but I'm sorry, but that time I had not thought about the format. I should have thought about it. This suddenly came to my mind, and I gave, but anyway, they had volunteered it. That time it was not even an assignment. They had just volunteered it to do it. So for the rest of the assignments, there will be, say, 10 students doing the same assignment, but only one group will be asked to present. That is what I'm trying to say. So you need not prepare the presentation as such. You can just submit the answers to the questions that are asked, and then we will see. Okay.
Yes, ma'am.
Ma'am,
Thank you.
these can be handwritten or even we can use LaTeX.
Yeah, anything.
Okay, ma'am.
Anything. You will get the instructions on the assignment. Okay.
Yes, ma'am.
You can type, you can handwrite, you can include graphs, you can include some animation, you can include some plots, like Suhas had included some plots. You can, what for explaining your answers, you can use anything. You can include videos, you can include images, whatever you want to do. Okay. It can be LaTeX, it can be handwritten, it can be a mixed version also. Some pages can be handwritten, some pages can be typed. There can be some graphs which can be the plots, and so the plots part can be the typed one. It will be a software, and the other can be your handwritten. So you can just try to make it as good as possible. That's up to you. Okay. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes.
I mean, it will be, the assignment will be something like a small project which you can complete in 2-3 days. Maybe not, I mean, you will not take it more than that, but it will be like a small project. That is, so I'm giving you long questions so that even if you work in group, at least every student is doing their part. And as usual, if you are doing it in a group of two, then you have to include the name of your partner on the cover page, and you have to also include the contribution of each of the partner, right? The way you had done it in your project last semester. Okay, fine. So even if you are doing it in a group, you can I mean, you can discuss it in among the group. Maybe you can but everyone has to submit. It is not that it will not be a group submission. Fine. So you can decide your partner and you can have a discussion, but it is not that your assignment report will be identical. It is not the project of that cap. You can work in groups, but when you are writing, write it in your own language. Fine. Is that clear?
Yes.
Yes, ma'am.
Yes, ma'am.
Groups is just for discussion mainly, so that you get to do some discussions among yourself. Fine. So we will meet at 2:45 then.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay. Okay, then goodbye.
Thank you, ma'am.
Thank you,
Thank
ma'am.
you,
Thank you, ma'am.
Thank you, ma'am.
Yeah.